He never graded it. But didn't show up. Wait. So does that mean I get 100 because he never graded it? No, dude, it doesn't work like that. Or else you would never like survive a year as a professor. Um, I'm not in the class, Joseph. No, I know. But imagine for a second, people would be like getting hit by cars.
Okay. Well, you still have to study, right? I mean, we only have 2 weeks. So make sure you ask your questions, right? If things don't make sense, please ask. Don't wait. You have no time to catch up from now on. Okay. So what did we do last time? Again, we say, well, if you're looking at the problem have these keywords like complex permittivity, conductivity of the material, loss tangent of the material, of the media, all that. That means you're dealing with lossy medium, or realistic medium, right? So the first thing you want to do is get on the calculator, calculate the loss tangent. If it's less than 1%, we say, oh, we are dealing with low loss medium. And right away you go to this table, which is going to be on your cheat sheet. I'm going to make your cheat sheet this week, today, right? So you look at this, you say, okay, this is for what we learned before when this is zero loss, lossless, no attenuation. Beta is just my K, which is omega over velocity, and velocity is 1 over square root mu epsilon. So all the formulas here. Eta is my wave impedance, is square root mu over epsilon. All this were, the equations where we used before. Velocity is 1 over this, right? Now we say for low loss, all these are the same. The only thing we have to do differently is to add on this attenuation. So for low loss, everything stays the same, except you must have exponential decay term, attenuation term, right? Remember to add that on. Okay. And the way you calculate it is just sigma over 2 times eta. You can calculate sigma by looking at the formula, right? So far, so good? All right, so now we're going to go to the other limit. What if loss tangent is not less than 1%, but on the other side is extremely high? How high? Let's say if loss tangent is greater than 100 or so. Again, this is not a digital step function, right? It's not like 101 is good conductor, 99.9 that's not good conductor. It's not like that. In reality, when you get loss tangents to be like 80 or something, you say, well, the power is good enough for a good conductor limit, right? But in the exam, I'm sure I would make it either less than 1% or greater than 100%. We're not going to deal with anything in between, just because it's more complex math and I don't want you to deal with it during the exam. Homework maybe, but not exam. All right, so what do we do when we are dealing with loss tangent that's greater than 100? We call this good conductor limit, right? Remember, we say good conductor, that means you try to propagate a wave in a good conductor. You want to send an electromagnetic wave in a block of metal. It's very difficult, right? It's almost impossible unless the frequency is so high we get into the X-ray region. That's another story, right? So a good conductor, that means it's really hard to propagate electromagnetic wave. That is, loss tangent is greater than 100. Okay, so this was the definition, just like what we had before. This is all given. And now we look at this. You say, okay, if this number is big, then I can pretty much drop the 1, right? 1 minus J200 is still J200, right? So if I drop this one, then I have a square root of minus J this, a single term. That's good. But wait a minute. What is square root of minus J? What is square root of J? What is J? Square root of minus 1. What is square root of J? Right. So you say, wow, I don't know. But if you rewrite J, what does J means to us? Is e to the J pi over 2, right? It's a phase shift, 90-degree phase shift, right? Remember, you have Ex is equal to cosine x plus j sine x. When x is pi over 2, cosine pi over 2 is 0. Sine pi over 2 is 1. So e to the I pi over 2 is just, yeah, I or j pi over 2 is just j, right? So if j is e to the j pi over 2, I take a square root. What's the square root of this? Half the exponent. So this is j to the pi over 4. That means the phase angle now is, instead of 90, becomes 45. What is the 45-degree phase angle? 1 plus j divided by root 2. This is square root of j. Right? Now you know how to take a square root of an imaginary number. Right? Are we okay? All right. So what is square root of minus j? Square root of minus j is the square root of e to the minus j pi over 2, minus 90-degree phase shifts. When you take the square root of it, you divide the exponent by 2, and now it's minus 45-degree phase shift. That's 1 minus j divided by root 2. Right. You have to remember that because this formula is in the cheat sheet, is in the table. So now what is gamma? You put square root of minus j with this. Now it becomes this, right? And then you have a j, you have 1 minus j, you simplify it, and then you have a square root of this. And we say gamma, the propagation constant, has the real part, attenuation constant, and the imaginary part, oscillations, the phase constant. But wait a minute, when you look at this, what do we see? The real part is this. The imaginary part is also this. Alpha is equal to beta. Only when you have a good conductor, alpha would be equal to beta. Okay, I would emphasize what does that mean and what's the consequences of this. And they both are equal to this. Alpha is equal to that. That's one thing. The other thing is eta. Eta is the wave impedance, mu over epsilon. Epsilon is the complex epsilon. Now, if I drop the 1, because this is so much bigger than 1, that becomes this. Square root of j, we say we know how to deal with it, is 1 plus j over square root 2, 45-degree phase shift, times the rest. Oh, the epsilon cancel. I was like, where is the epsilon? Okay. Right, so now I have this 1 plus j of this, again, I have 1 plus j. What does that mean, right? If I simplify it, this is just alpha over sigma. Doesn't matter, you can rewrite it either way, that's fine. But 1 plus j, meaning eta is a complex number, and the phase angle is 45 degree, right? 1 plus j is 45-degree phase shift, right? Right? So what does that mean? Well, remember what eta is? Eta is E naught over H naught, the ratio of the amplitude between the electric field and the magnetic field. Now this one carry a 45-degree phase shift. So what does that mean? The electric field and magnetic field, they're no longer in phase. Now they have a 45-degree phase shift. Okay. But to us, as far as solving the problem, we don't have to remember this. We don't have to care. We still say E and H are in phase. And then when we calculate the amplitude, the eta would get into the calculation. That means the phase angle would get into the expressions. You don't have to remember it. You don't have to do anything. You just keep track of the math. Are you with me? I'm going to do examples to explain that. Are you with me? Okay. So far, so good? All right. One thing you have to remember. Alpha is equal to beta. What does that even mean? right? Alpha is attenuation, beta is oscillation. In the past, when we're dealing with lossless medium or low loss medium, what is beta and how do we calculate it? Tell me. Beta is my K. It's like omega over the velocity, right? Right? And the velocity is C over N. So if the frequency is given, the material is given, beta is given. It's not up to us. But now we say, no, wait a minute, beta is a different number. It's oscillating at a different frequency. Oh, different wavelength, I should say, not frequency. Okay, so this is the part you have to remember. When you're dealing with low loss medium, you can still use this equation to find beta. When you're dealing with good conductor, this equation no longer works. In fact, anything that has to deal with index of refractions, you cannot use that anymore for good conductor, right? Because you cannot talk about the light would bend inside a metal. It doesn't happen that way, right? The refraction has no meaning now when you're dealing with good conductor. So can you remember that? Let me rephrase this one more time. Once you know you're dealing with good conductor, do not use any equation that has an N in it, that has an index of refraction in it. Do not use it. I don't care what equation you have. Velocity is C over N. Nope, you cannot do that. Okay. Are we okay?
Does omega over K still work as long as you use the right?
Omega over K. No, because then K will be complex. Let's see. So the velocity becomes this is just our alpha beta equations. Right. No, we shouldn't even, or I wouldn't even ask you what's the velocity of the wave because normal electromagnetic wave doesn't propagate in the good conductor, period, right? All right. So we're going to do example. Remember, good conductor need a special care. Before we go on, we have a couple of definitions we need to talk about. One is skin depth. Okay. What is skin depth? Well, we just say if I have a block of material, if I want to send an electromagnetic wave in it, this electromagnetic wave would decay really fast, exponentially fast. The higher the frequency of this wave, electromagnetic signal, the faster it will decay. You know, the better conductor, the faster it will decay. How fast are we talking about? Well, that's the distance is measured in terms of skin depth. So how do we define skin depth? If I'm looking at my exponential function, right? And if I define the distance is equal to 1 over alpha, where alpha is my attenuation constant. And this distance is how we define it as the skin depth. The skin depth is defined as 1 over attenuation, which is sometimes written as a delta with an S, sometimes we don't, right? A lot of times we don't. But again, when you see delta, never confuse that with the loss tangent delta, right? Like I say last time, no one would break this delta off the tangent. No one would ask you what is this phase angle ever. They will only ask you what is the loss tangent of the material. Okay, so when you see the delta by itself, it's never the loss tangent. It's always the skin depth. Is that clear? Right? In the exam, I see a lot of confusions here. So make sure you remember this. All right. So what happened when the distance is 1 over r? Well, then when I look at the attenuation, e to the minus alpha r, where r is equal to 1 over alpha, that's just e to the minus 1, right? So if I put e to the minus 1 here, or this is equal to 1, and when the distance is equal to 1 skin depth, the electric field intensity would drop by 8.7 dB. 8.7 dB is roughly about 1/10, like 10% or 12% of your original signal. Pure skin depth, minus 70 dB, that's already almost like 1/200. Right? It's getting smaller really fast, exponential fast. So the higher the frequency, the shorter the skin depth. So this tells us how much signal or the electromagnetic field would can penetrate inside the material. So you say, what do I care? I mean, I'm a double E. I don't really care. I don't need anything inside the metal. Yes, you do. So questions that people will ask you because you are the double E, you are the one that make the call. Then you make a PC board, a circuit board, right? And then you have, let's say, copper plating. How thick do you want your copper plating to be? I don't know, whatever thickness you have. No, because they have different thickness for you to choose from. So what's the difference? Well, the thicker it is, the lower the loss, but the more expensive it is. Because gold and copper, they're not cheap, right? So you say, well, the thinnest possible one. No, that's not true, because if it's too thin, then the signal would penetrate right through it, and then you will be more lossy. So what is the call? Right? So you get online, and there's something called skin depth calculator online. You don't have to remember the formula, but they tell you what the skin depth is, and then you say, well, roughly at least 5 to 10 skin depth, that's perfectly safe. 5 skin depth, that's like more than almost 100 dB already. So it's like 1 billion of a signal would be gone. 1/1 billion would be left. So it's like if I have 1 watt, I will have like 0.19 of watts, something like that. So is that's good enough, right? Or remember someone talked about EMC, right? What is EMC? When you make any device that has an AC circuit in it, your electromagnetic wave will radiate. And FCC say, well, you cannot radiate any signal out because you're going to interfere with other signal, the ambulance, the police, the military, whatever, right? It's going to knock on your door. So they have a very strict requirement. Let's say minus 120 dB, for example. What does that mean? That means the signal must drop like 10 to the minus 12, that much, right? So, but how do you keep that signal enclosed in your box? Well, you have a lot of things, a lot of tricks, put conducting ink, or you put a lot of screws, and then one of the question is, well, the box is part of your cavity, also will give you loss to your circuit. So a lot of times we have the plate, like silver plating or gold plating, the housing. Again, people would ask you how much gold you want to plate on the housing. So, well, as much as you want. No, because it's expensive. You're gonna, right? Your company is gonna lose everything. So is that why as thin as possible? Well, how thin is thin enough? 5 skin depth, 5 to 10 skin depth would be more enough, right? So and who would they ask? You, because you are the double E, right? You are the one who knows how much loss can I withstand, and So yes, you do need to know this. All right. General material. So before I do an example, I want to point out 2 things that usually is very confusing for students, right? One question is, I keep using K and then switch to beta. Why? I mean, are they the same? I keep saying that they are the same, but they're not really the same. What's the difference? So I don't come up with this notation, okay? So K is what we use, which is your free space propagation, the wave vector. That's always true. But when we are talking, when we are dealing with either the waveguide or the optical fibers or when we are dealing with lossy medium, a lot of times people use beta, like here. Beta only means the oscillation part, which is just the K. But if I would restrict myself to a one-dimensional problem, then beta is just what the K in the signal propagation direction. So let me repeat. So K is a wave vector, right? It's how the wave oscillating and propagating. And in general, it's a three-dimensional vector. It has X components, Y components, and Z components. The convention a lot of times is we take the Z components, if this is inside a waveguide or the optical fibers, we say if the signal is going to, or the coaxial cable, if the signal is going to go to this direction along my guide, then this is my Z direction. Even though the wave inside would be like wiggle and bounce all over, the K would be all over the places, but beta would represent the propagation of the signal along the fiber or along the waveguide. Okay, so in that case, beta is the Z components of K. You can think of that.
Like a drift velocity?
Huh?
Like a drift velocity?
Like a drift velocity of an electron's current, for example, if you like, right? So that's where, but to you, you should always think, well, it's beta, the beta is really the same as K. Unless your K is a three-dimensional problem, like we are going to talk about it, then you need to take beta as a vector, and which has the beta magnitude, and the direction is my K direction. I know it's kind of complicated to say it like this. Okay. So as far as we are concerned, you can always think beta and K are the same, unless it has more than one dimensions, then you need to think beta more like a K. We'll do it in another example. The other question was alpha. So we deal with that last time. We say e to the minus alpha r, but how do I deal with that, right? What does e to the minus r mean? E to the minus r means if I'm propagating along inside the lossy medium, whatever the distance I travel, the amplitude would decay. So r is the distance the wave would travel in this medium, right? So imagine my k is not a simple along a z direction or x direction. It's propagating in this k direction, which has an angle of theta with respect to the y-axis, right? So this is my k, what is k, the direction of k hat? So if this is theta, then cosine theta would be along the y direction, sine theta would be along the x direction, right? At this point, you should be able to read off your diagram and write this correctly, right? Right? No question on this, right? If you do, see me, please. All right, so now what is e to the minus alpha r? If I think alpha, if I think r is the distance the wave travel, then r would be just the length of this. What is the length of this? If this is x, this is y, then alpha, then the r would be square root of x squared plus y squared. Correct? Okay. But last time we say we can also take r as k hat without the hat. So that means I can write this as x sine theta plus y cosine theta with no hat. Make sure you don't write hat on it because I will take points off. If you have hat on the exponents, if you have hat inside the cosine and sine function, I will take points off. Okay. So are they the same? Are we free to use either one of them? Well, they are the same. So let's look at it. What is x sine theta plus y cosine theta? X is x sine theta. Looking at this triangle, sine theta is x over r, right? Cosine theta is y over r. So now I have x squared plus y squared over r. R is just the square root of x squared plus y squared. But then this is just equal to square root of x squared plus y squared, which is just equal to r, right? So I can write r just like that. Remember what we say last time? If I want to write e to the minus r, one easiest way to do it is write e to the minus alpha. I know alpha because I calculate it. And then write r as the k hat without the hat, which means it's really just r. Okay, get it? All right, so let's do one example. Let's do an interesting one. You need the equation. Did you write down the good conductor equation?
What's the one?
Alpha, beta.
Yeah,
Okay.
and the eta c.
Yeah.
Yes.
Okay. Good. So let's say I'm going to do one like what we did before. At t is equal to 0 at the origin, I see my electric field along the x direction with 2 volts per meter. Just like what we had before. And this is a left-hand circular polarized wave. The skin depth is 100 millimeter. No, that's a lot. Sure, why not? Let's do a little smaller one. 0.1 meter. Signal is what else do you need to know? Can you see the formula? Frequency, get it. Mu sigma, loss tangent. Okay. Alpha and beta. Alpha. Where's alpha and beta?
It's there. It's alpha equals beta.
Oh, mu sigma. I think that part is all I need to give you. If I need to give you more, I'll add on it later. So the question is, of course, to find h, right? And then the next question is, how long would the signal travel before the signal drop 100 dB? 100 dB, that means 10 to the 10 power. It drops 10 billion times. Okay, so it's very small. How long would it drop? Okay, there we go. So what do I do? When I look at this problem, what's there now? Skin depth. What does that tell me? It's a lossy medium, right? Remember, if you see one of those terms, you know, the conductivity, complex permittivity, loss tangent, and skin depth, that tells you it's a lossy medium. Not only I know this is a lossy medium, I know this is a good conductor because it has a skin depth. No one would talk about skin depth for low loss dielectric plastic, no, right? It's only for good conductor we will have this term skin depth. So that means automatically this is a good conductor limit, right? So right away I look at my formula sheet and it say alpha is equal to beta is equal to square root of mu sigma omega over 2. And then eta is equal to 1 plus j square root of mu omega over 2 sigma. Is that right? Okay. Right? All right. So where do I go from here? Where do I go from here? This one is not, I don't think I have it on my cheat sheet. How do I get alpha or beta? Do I know sigma? I don't know sigma. I know frequency, right? But how do I get sigma? I don't, right? Then what do I do? Then you have to remember what skin depth means and how do we define it? How do we define skin depth? 1 over alpha. So knowing skin depth is 0.1, that means alpha is equal to 1 over 0.1 is equal to 10. It's equal to beta. Is that clear? You have to remember the definition of skin depth is 1 over alpha. It is a good conductor. This part is not going to be on your cheat sheet. All right, so once you have that, then I can go back and can calculate what sigma is now, right? So what is sigma? If I'm going to use alpha, then it's alpha squared times 2, and then divided by mu naught, divided by omega, that would give me sigma, right? Just from here. And so 2 alpha is 10, so it's 100 divided by mu is mu naught because we are not dealing with magnetic material. So this is 4 pi times 10 to the 7. And then omega, what is omega? 100, 1,000, what is omega? 10 to the 10. So if you multiply by 6, this is probably about 10,000. 10 to the 4, 10 to the 4 plus 10 to the 6, 10 to the 10. If you don't remember, then spend your couple minutes on your calculator. The idea was if you would do a few of these problems, then you probably remember how to do this without using a calculator. Okay, so what do I have? Help?
You said you didn't do.
Well, I have 1 over pi, right? I need the 1 over 2 pi. What is 1 over 2 pi? And then this is 17, 10 to the minus 15.
1 over 2 pi is.
Oh, wait a minute. Mu naught, is that 10 to the minus 7 or 10 to the 7? 7? Minus 7. Yeah. So it's 3, 1, so it's 0.1. Yeah, so what is 1 over 2 pi?
0.16.
So this is 0.016. Right, assuming it is correct. Right? Okay. So now I can put it in here to find eta. So watch carefully. How do you deal with 1 plus j? So eta is equal to the magnitude is this. So I have a 2 here. Really?
I think so.
Okay.
And someone else can.
Mu naught is 4 pi 10 to the minus 7. Omega is 10 to the 10. And then divided by 2 divided by 0.016 and then take a square root, right? And then 1 plus j, what is 1 plus j? 1 plus j is square root 2 with a 45 degree, right? Let me do that again. 1 plus j, what is 1 plus j? That the magnitude is square root 2, the phase angle is 45, right? So that means this cancel, and what is the magnitude here? Anyone? 4 pi divided by 0.016 times 1,000 square root. Huh? 64? 604? Right? You guys get the same thing? Yeah?
Got 886.
886 you after the square root?
Yeah. 886. Why didn't you- Well, I didn't. Well, I didn't cancel out the two in my. Oh.
Eight hundred and 86.
Sigma? 0.06. What did it be six? Or sigma? No, it's saying sigma equal to 0.
Any questions so far? No? Okay. So now I need to tell you what's the wave propagating into, right? So any preference?
Beeswax.
Huh?
Beeswax. It's on the table.
K direction.
Oh, exactly.
X hat? No, X hat is already here. Say minus C hat. It's propagating in the minus C direction. Okay. Given. Should have given, but I didn't give it to you. All right, so now we are ready to write, we want to find H, but let's find the E first, right? E1 first. Okay. You ready? What is E1? The direction is it's given. X hat, right? Magnitude is 2, right? Right? You're following me, right? X hat 2, because this is E1, so it's cosine. Omega t, what is omega? 10 to the 10, right? Minus k dot r, what is k? Omega divided by velocity, yeah? Yeah?
Let me just didn't really find it.
We already say we cannot do that. This is good conductor. We cannot do that. Right? We don't need to find k. What is this? This is my beta. This is my beta. What is beta? Beta is the same as alpha, 10. So 10. What's the direction? Minus c hat. So this is plus 10c. Are you with me? Right? Do not calculate k or beta or anything here. I mean, we calculate. I mean, do not calculate omega over v. That only for low loss or lossless. Right? Remember that, right? So anything else? Other than unit, what's the unit? Anything else? This is it? Yeah? Yes? Yes?
Polarized.
This is law C medium. So what does that mean? We must have one term, attenuation. We must have e to the minus alpha r term.
Said it 3 times.
Right? But for good conductor, this is minus alpha r. Alpha is the same as beta. The r is the same direction as the k hat without the hat. So this term should be the same as my attenuation term for good conductor. Huh?
Positive.
Positive. Because this, my K hat is negative.
But where's the attenuation? Shouldn't it be a
Didn't
negative?
you say it's K?
So that's a good question. Okay. So the question was, wait a minute, we say exponential decay, right? But now this is positive. Does that mean exponential increase? Huh?
We're going negative.
We are going to the negative direction. So yeah, exponential decay going to the negative direction. Right? Nice catch. I hope you can remember this, right? For good conductors, this term is always the same as this term, always. Doesn't matter how complicated it is, they're always the same. So this is E1. And let's look at, again, I asked you to find H, so we don't need to find E2, right? We can just go directly to H1 and then goes from H1 and H2. So I see a C and an X here, so I'm gonna do X and Z, and then my Y would be in or out. In or out. Right? Okay. So my E1 is along the X direction, and this is my E1. My K is minus Z direction, which is going down. Where is my H1? Out? Is that out? Okay. So H1 is out. So that means it's minus Y hat, right? So H1 is minus Y hat. The amplitude. Okay. So we say E naught over H naught is eta. So H naught is equal to E naught over eta. And E naught is 2. What is H? Oh, what is eta? Sorry. A86, 45 degree. Two divided by A86 is let's say 2.3 with minus 45 degree, and it's milliamp per meter. Okay, so I'm going to write 2.3 and milliamp per meter, right? This type of problem, make sure you write the unit, because if you don't, I'm going to take points off, as you probably have seen in your homework now, right? Because of this reason, because are you writing it as amp per meter or milliamp per meter, or right? So, okay, so that's the direction, that's the amplitude. My exponential function will stay the same, right? And then the phase, we say they have the same phase, will stay the same, except my 2.3 has a minus 45 degree. I need to absorb that minus 45 degree in here. So what do I write? I write minus 45 degrees pi over 4, right? Don't write degree. I know in your homework solutions, the book use degree, but nobody write it in degree. It has to be a pure number. Okay, if you do that in the exam, sorry, I will take points off. Again, this part is the same as this part. Make sure you check. And then you're done with H1. It's really not that hard. this problem, actually, if you think about it, is not the simplest problem, right? Is a good conductor, is lossy medium, is circular polarization, is not pure polarization. And, but now you know how to do this. If you work along with this example, it's really not that difficult, right? So when you go home, please redo these examples, okay? The way you want to study for the exam is always redo all the examples we did in class, and then make sure you redo all the homework, the assigned homework, and then redo all the homework that are assigned on the extra credit. If you can do that, you should do well. And if you want to get 100% every time, what did you do, Joseph? He did every single problems in my book for no credit. He didn't get extra credit for that, but he did every single one of them. If you would do that, you probably get 100% easily. Are you willing to do that? It does take time.
There's only 10 problems for plane waves.
Yeah, huh?
There's only 10 problems.
I know the next few chapters is actually shorter, right? It's only 10 problems. Yeah. See, it's not too bad. So now we have H1. So if you don't get 100%, I know you didn't do all the problems. What? Huh? Huh? No, because it's negative, right? Positive in the denominator. So when you put on the numerator. Oh, no. So this phase shift is like e to the pi over 4. You just add on to this e to the minus j pi over 4. Yeah. Yeah. All right, H2. H1 is coming out. Where is my H2? Well, remember this is a left-hand circular polarized wave. So what does that mean? I need to use my left hand. I need to go H1 cross H2. The thumb is always my K, so the thumb is down. H1 is that out? We say H1 is out. So where's my H2? Right? Going to the right, which is the X direction. Are you all agree? Right? If you don't, please come see me. Don't wait. Right. So H2, right away.
Got normal X hat,
Huh?
right? Positive X.
Yes.
Okay.
X hat. And then what's the magnitude? Same. How do I know the same? They're the same. Circular, right? Circular means they are the same. And then same attenuation. This is cosine, so this one is. Don't write cosine again. Some people did, right? This is sine. And then the rest should be the same. Milliamp, don't forget the unit. And you're done. Any questions? Yes.
Can you explain how you get, so when you say your 10z for your exponential, right? That e to the
Yes.
10z.
Oh, 10C, I forgot.
Oh, no,
But I write 10C. I mean e to this.
it's the same as where you take k hat and then make it negative and then with the hat, right? You have to make it negative.
Yes.
Okay. It's not just k hat.
Well, it's minus alpha and then k hat without the hat. So this is minus c hat. Without the hat, it's minus c. So that
Oh,
becomes
gotcha.
positive c. Any questions? All right. So the last question was, how far would this wave travel when the signal strength would drop 100 dB, 10 billion times, right? So what do I do? This formula is in the cheat sheet. Hey, where's my writing thing?
Click on the erase.
Why erase it? Okay, so attenuation in dB is equal to, I don't write the negative, but some people do, is 8.686. This is in your cheat sheet, alpha out, right? I usually don't even write this because it's implied you drop 100 dB. You don't gain 100 dB of signal. You lose 100 dB, right? So this is 100 dB, or if you keep the minus, then you should be minus 100 dB. Is equal to 8.686 times alpha. Alpha is 10 here, and R is my Z, right? The directional R doesn't matter you want to call R or Z, doesn't matter. And so this is 100 divided by 86. 1.15 meter. I travel about 1 meter, about that long. Then they drop 10 billion times the signal. Okay. Questions, questions, questions. No questions? Okay. Before I do the next example,
How do we get to time from,
time.
because I think we were looking for how long until 100 dB drop.
Oh, how far I should say.
Oh, okay.
Did I say how long?
I think
Yeah.
it's-
So how we do that?
We have
Oh,
to find this as a function R or something.
I didn't write it to say that. Okay. Base times are equal. All right. So going next. I don't think I have time to get into the chapters that I probably should, but I won't have time. So the next chapter is supposed to be, okay, now I have a signal traveling and hit a boundary, boundary condition type of problem. Then some of the signal is going to be reflected, some of them is going to be transmitted. This is like a physics 52 type of problem, right? And based on what we learned, the Maxwell equation, the boundary condition, we can derive Snell's law from here, and 1 sine theta 1 is then 2 sine theta 2. And we can answer questions like, how does the polarized sunglasses work? Why we paid a few dollars more. We can answer questions like, why we have a difficult time finding the Malaysia airplane on the bottom of the ocean where the black box is, emitting a signal. How come we cannot receive the signal, right? Because of the attenuation, because of the angle and all this. So it's not difficult, but it does take at least a couple of lectures to go through this. And I don't really have a couple of lectures left because I need to save time for transmission line. But I do want to talk about what happened when the wave hit the boundary. So I'm going to restrict ourselves to the discussion of what we call the normal incident. So if we have a boundary here, the signal travel perpendicular to the boundary and reflect perpendicularly and go into it perpendicular. So there's no refraction, there's no angular dependence. But based on that, we still can learn something about the nature of the power being reflected, transmitted, and whatnot. So I'm going to do that next. And the reason we want to do this is also because this ties to exactly what we're going to do in the next chapter, the transmission line. The transmission line problem It's very similar, except we focus ourselves onto like a PCB or waveguide type of problem. And then when I connect different components or devices with the transmission line, what happened to the signal, right? This is a change of impedance. Some of them will transmit, some of them will reflect. The way we treat that is exactly the way we treat the electromagnetic wave in the normal incident case. So I'm gonna just do that. It shouldn't take a lot of time. Any questions so far? All right, so allow me to pull that up. How do I use a full screen? Okay, fine. So we're gonna skip all this. Let's just look at this. Normal incident. Now let me set up the picture correctly. So we're saying on this side is one medium. I call it with N2 index of reflection. This is N1. And the reason a lot of times I use index of refractions instead of using eta 1 and eta 2, the wave impedance, they're really describing the same thing, except the index of refractions give me a little bit more physical intuitions. So for example, what is the index of refraction in air? 1. What's the index of refraction of water? 1.33, 4/3. What's the index of refraction of glass? Depends on what type of glass, but it's roughly about 1.5. And then diamond is higher. So what we can see is as the index refraction go higher and higher, the density of the material go higher and higher. So that gives me a kind of understanding of, well, if I have a material, the ceramic is really hard, then the index of refraction would be harder. Then I know how does the wave reflect it? How do they supposed to behave? Doesn't matter, you can always convert it one to another, right? How do we convert it? Because eta is equal to eta naught over n. So eta and n, they're related, inversely proportional. All right, so suppose I have a electric field propagating, gonna hit this medium, hit the boundary. Ki is the wave vector of the incident wave, so going in onto this interface. Suppose my electric field is coming out, okay, then my H field must be pointing down because E equals H is K, right? Okay. Now, if I know that, then I should be able to, if I know only one of them, if I know E field, and then you can tell me what H field is already. If I know the incident electric field, you can tell me what's the reflected electric field by knowing the medium. And that's what we want to figure out. So once we know one thing and knowing the medium, we know everything about this signal. Okay. So when the signal coming back, the reflection, of course, is going the opposite direction, right? And assuming E is the same direction, pointing out, that means the incident wave and the reflection wave are in phase, assuming. Then H would be pointing up, right? Because E equals H is K, right-hand rule, right? Are you following me? Okay. Then, and so is the transmission, the electric field is coming out, the wave is propagating this way, then the H field is that. So one thing I want to point out here is a couple things. One is we say the E field are in phase, the reflections and the incident in phase. Are they always in phase? No, but we assume they are, and we write the formula that way. If they are not in phase, my calculation will give me a negative sign or carry a phase, and I'm just incorporate that into my phase shift. right? So just like what we did before, we assume E and H are always in phase. Even when E and H they're not in phase, I still assume they're in phase. The eta would carry the 45-degree phase angle, and that would go into my wave, right? Are you with me? Okay, so remember E fields are always in phase. Okay. But if E fields are in phase, then H fields are always out of phase, right? Because H incident is pointing down, H reflection is pointing up. If the E field are in phase, the H fields are always out of phase. Remember this statement. Later on, we're going to look at the same thing again in terms of voltage and current in the transmission line. When the voltage are in phase, the current are out of phase. The voltage is associated with electric field. Current is the magnetic field. Okay, we'll go to that when we get there. But I want to remind you this concept keep coming back. Okay, E field are in phase, magnetic field are out of phase. Yes.
It's only for the reflection and the.
Right, the transmission is always in phase. Always. If you, right, there's no if, no but, the transmission is always in phase. It's only the reflections we have to worry about. Okay. So without knowing any detail, I can write, if I call this z-axis, call this x, that means y is coming out, right? Y is coming out. So the E field is coming out, they have y direction, have some kind of incident magnitude, and has a traveling wave traveling to the positive C direction, right? And we can just write the general formula for the H field, for the reflection also, right? The same because they're in phase, but then this is plus instead of minus because one is going to positive, one going to the negative same direction, right? The K would be different. The K is 2 pi over lambda. The lambda in this, the wavelength in air or in this medium would not be the same as the medium wavelength in the other medium. So the K can change. Omega, we assume they can be different, but later on we show that they are really the same. This is one of the things that we learn in physics 52, the frequencies do not change. A yellow light will still stay in yellow light when you get into the glass or reflector. It won't change color. Okay. Yeah, this is one of the statements. So now the boundary conditions tell us as z is equal to 0, all of them must be the same. And in order for them to be the same for any given time, that means all this frequency must be the same. That's one of the reasons, one of the proof to arrive to that conclusion we learned earlier. And now I can do the same thing. I can do the same thing and write, if this is the electric field incident, I know how to write this H field, right? Because E equals H, so I figure out the direction. This is minus X direction. And then same phase, and then I know how to calculate the amplitude. E over H is eta, right? So you do that, you can write all 6 fields in general, right? I'm not going to do that in detail. Go home and do it. These are all within your capability. You all know this very well. So let's do that. Now, we have all the 6 fields, and what we're going to do. Now we look at the boundary conditions. In the boundary conditions that we learned. So what is the boundary condition? One of them is, if I look at the electric field, ET1 is equal to ET2, right? Remember that? Boundary condition. What does that mean? The electric field tangential to the surface, in this case, the X or the Y direction. Let's say Y, because electric field is pointing one. The electric field on this side is equal to the electric field on this side. What's the electric field on this side? Well, I have two. One is the incident, and then one is the reflections, right? At this location, they add up. So EI and ER at R is equal to 0 will add up on this side. And ET when R is 0 will be on this side, and they must be the same. Right? That's the first boundary condition. Right? Say yes. You heard about boundary condition before. So that means the incident wave amplitude and the reflected amplitude right next to the boundary must be equal to the amplitude on the other side. Right? So that's one equation. The second equation, the tangential field, are also the same. So we have n cross h1t minus h2t is equal to js, but we are talking about the dielectric material between the air and glass. There's no current on the glass, so this is 0, and this is 0, that means these two tangential are the same. Right, so that means the tangential field on one side is equal to the tangential field on the other side. This is negative because remember H field are out of phase when the E field are in phase. So when they are adding, this one is subtracting. Right. But H is equal to E over eta because E over H is eta. So I can write this in terms of E. Right? So this is one equation, two equation, and then I combine them. So based on the first equation, I multiply eta 1 on both sides, and then I bring the equation 2 up here, eta 2, eta 1 here, and then I can add them together to get rid of R, and then subtract them to get rid of I, for example, right? So when I subtract them, I get rid of the I, and no, I just make them equal for the first one. I say these two are equal, so that means this is equal to that, right? And then I just bring by eta 1 E naught I plus E naught R is equal to eta 2 E naught I minus E naught R, and then you cross cut, you massage it, you get to this expressions. You can write E naught R over E naught I. Right. I missed a couple steps of algebra. You can fill that in. But I want to drive to the answer and tell you what the answer means, and then how do we use the answer. So E naught R is a reflection amplitude. E naught I is an incident amplitude. So what does this fraction tell me? This ratio tells me what is the fractional electric field will be reflected. Let me repeat that. If I know the incident electric field strength, I can tell you what's the reflected electric field strength. Just based on the material. If I know what's the material number 1, what's the material number 2? Is it air, glass, air, water, air, PCB, whatever, right? If I know the material, I can tell you how much signal is being reflected, right? And this is called gamma. Gamma is called the reflection coefficient. Okay, so again, if I know the material, I can tell you what's the reflection coefficient. And based on the reflection coefficient, I can tell you how much power is being reflected, how much power is being transmitted. Okay. And then now if I massage that equation a little bit more, now if I want to get rid of this, so if I add these two equations, this would, no, this won't cancel. Now, if I want them to cancel, I take the first equation again, I multiply with eta 2 again, bring this equation, there's the same equation. Now when I add these two together, this goes away. So I have a function of transmission, right, with respect to incident. And so I can rewrite it. I can write the transmission amplitude over the incident, and that is equal to this. This is what we call tau. which is transmission coefficients. What does that mean? That means it tells me what's the fraction of the signal would be transmitted. Like 50% would be transmitted, or 30% would be transmitted. Right? And here, tau is the same as 1 plus gamma for our special case. So how do I understand that? So here, if I divide everything by E naught I, E naught I over E naught I is 1. E naught R over E naught I is a refraction coefficient. E naught T over E naught I is the transmission coefficients. So if I know the refraction coefficients, to find the transmission is very easy, just 1 plus gamma. Right? And do you remember you have learned something about thin film interference in physics 52? Like when you see a bubble, when you blow a bubble, soap bubble, you see this color, rainbow color. Why do we see different color on the surface? Or when we look at the ground with grease, with oil, and we see different color, right? Why do we see different color? Right? Because of the thickness, because of the dielectric constant, and because it's a double reflection. Do you remember something like that? Do you remember something called Newton's ring?
It's the same way a rainbow, right? The water drop.
No. So let me talk about, I'm going to talk about Newton's ring for two minutes. So we have a thin film of oil, the light coming in is going to reflect off here. And then because this is so thin, that the reflection from a second layer also come at about the same angle. So looking at here, when I receive two signals, if they are in phase, they add together, so I see a bright light. If they are 180 degree out of phase, they cancel. I don't see anything, right? So we see this interference pattern, right? Remember? So I want to talk about Newton's ring because if you go to Exploratorium at the dark corner, there is one display. But I went to a machine shop, a friend's machine shop. Here's a glass ball, not really, it's a cheap glass, it's not crystal. And then he put it on top of a desk, has a glass on it, and the light is not controlled, it's just fluorescent light. And then when I look in down here, I see the Newton's ring. So what is Newton's ring? So if you zoom it up, when the lights come in here, reflect, right? So if this distance here is a certain condition such that these two reflections are constructively interference, then I see a bright light. When they are destructive, I see a dark light. So I see a bright ring, a dark ring. So I see this is what Newton discovered, so-called Newton's ring, right? Why do we care? Why do we want to look at the Newton's ring? So remember how we make glasses. Your glasses, we all assume is a spherical surface, right? What does that mean? That means this is a perfect sphere, right? That's why the lenses, camera lenses, so expensive. Perfect. How difficult it is to make this perfect? Super difficult, right? Especially in the old days when people are sanding it, by hand. How do you make it? And how do you check it? How do you even check it? Well, by putting it on another piece of glasses and look at the ring. If the ring is like concentric, right? Then that means it's even. Otherwise, you'll see more like a map. This kind of pattern, that means it's not spherical. It's not. It's just not right. And then you keep polishing until you get this ring. I thought it was very cool. But anyway. So the idea of looking at, well, do I see the bright color or do I see the dark color, has two conditions. One is the thickness with the index of refraction. The other one is this reflection in phase with respect to incident or out of phase? You kind of remember that, right? But you probably don't, right? So if they both are in phase, this is in, then these two are in phase. If this is in phase of this, out of phase, then these two are out of phase, right? If they both are out of phase, they're still in phase. No, don't remember. It's time to hit your physics book again, right? Okay, thin film interference pattern. So next time we're going to do a problem, including the boundary, including lossy medium, including the circular polarization, everything. We just do 2 problems and that will be it. Any questions? No questions? All right, good. Come see me if you have questions, if you want to talk more. See me.
It's something there, like a, like an actress, it's